that I'm here, so you can ask me questions if you want, if there's anything left over. And don't forget, this is the last question session because there is none tomorrow. So if you have questions about tomorrow's classes.
Andre, maybe I'm getting something wrong, but so the electron, muon, and tau neutrino doesn't exist. So what exists is the mass eigenstate. So we can have any linear combination of this mass eigenstate. But how we know there is only 3? Why some more than 3? Because we don't measure this.
So those are 3 linear combinations we call the electron, muon, and tau neutrinos. They're special because of the interactions. So it turns out that that's what the W boson does. So it's the couplings of the W boson that are identifying these 3 linear combinations, the electron, the muon, and the tau neutrinos, as special. So the interactions are the guidance for what are the special linear combinations. You can build any linear combination you like. The problem is nature does not know how to produce that particular linear combination. So that's why those are very specific ones are special, because that's guided by the weak interactions. If you invent a new version of the weak interactions, they can favor a particular different linear combination of neutrinos. People talk about gauging other global symmetries of the Standard Model. So people talk about U1 L mu minus L tau. You know, that could be a scenario where the linear combination you care about is a 50-50 mixture of mu and tau, and you can rewrite that in terms of mass eigenstates again. And that could be special in some way. So for example, Pedro showed you these non-standard interactions, the very generic ones. They are totally off diagonal. And you could ask yourself, is that coming from some fundamental new force that couples to different linear combinations of mass eigenstates? And that might be one way of understanding how this is going on. Yeah, this is a very good question. Just one aside related to that. There's another particle that couples to neutrinos, which is the Z boson. So you could ask, doesn't the Z boson favor specific linear combinations of electrons, muons, and taus, or 1, 2, and 3? The answer is no. The Z boson is totally democratic. It couples the same to neutrino number 1, or neutrino number 2, or neutrino number 3, or the electron neutrino, the mu neutrino, or the tau neutrino, or any particular combination that you like. So the Z boson is totally democratic, which means that you can always describe it in the mass basis, and it's always a 1-1 coupling, and a 2-2 coupling, and a 3-3 coupling. Or you can describe it in the flavor basis, and it's an E-E coupling, mu-mu coupling, tau-tau coupling, and so on and so forth. So the Z boson is extra special, but we already knew that because that's what happens in the quarks as well. The Z boson does not discriminate with respect to flavor. It couples to all the flavors in the same way, which is a very, very important statement. So that's why you don't have a flavor-changing neutral currents. And that's why messing around with the Z boson is really difficult. Because once you start doing that, you end up with some very, very large flavor phenomena that are ruled out by experiment. And people who work on, say, different Higgs models and extra gauge bosons and so on, one of the first things you worry about are flavor physics constraints, because you screw up this democratic behavior of the Z boson. Yeah. Stereoneutrinos make life much more interesting. And that's one way to mess around with the Z boson, is to add a stereoneutrino. Then all of a sudden the Z boson is not democratic anymore. So you have these flavor-changing neutral currents, for example.
Ferdinando, you showed an example of a stereoneutrino model for dark matter, which is not favored by the data. I'm curious if there is some models that are favored, or
yeah, there are plenty of models where you can. So this vanilla type 1 seesaw mechanism, which is the Lagrangian I wrote. this one. So if this guy is a KV stereo-neutrino or a stereo-neutrino, then is, and this guy is produced, so if, two ifs, if it's the mass is KV, second if it's produced via oscillations, then it's ruled out. So if I remove any one of these ifs, it's already okay. So imagine if I build up more things on top of this Lagrangian, then I can do many things. So if I go beyond this, then I can play around much more. Does that answer?
Yeah, but do you still have physical motivation for production of this?
Yeah, so yes. So actually these guys, if they are heavy, much heavier than KeV, you can more, I would say more naturally explain the active neutrino masses. So if you, I didn't know that, for instance, let's say that I don't care about KV stereo neutrinos. You're just building a model, I don't care about data. I'm touching this model for the first time in my life. So when you build up the models, oh, okay, maybe this guy has to be really heavy so I can explain neutrino masses more naturally because the couplings involved are not so small. I want this guy to be heavy. So this is what I would expect by construction. So not KV. I can push down to KV if I want to, but I don't have to. Okay, so more naturally I expect this guy to be heavy. And there are actually models which are based on gauge principles which predict the existence of heavy guys like this one. So from first principles, you can build up this Lagrangian.
Thank you.
About non-standard interactions, in the discussion that we have now, about the mass against states, they are the real interaction states and the real neutrino states. But in non-standard interactions, people define the coping constant using the flavor states, and the right way to do that was not should be through mass states. I don't know if.
I think André would not agree with your statement that you use the word real states to talk about electron and muon and tau neutrinos, and well, these are the states that interact, but they are not the real particles.
Yes,
right?
You can say real particles.
So yeah, I think your question is. If we can put, when you put the non-standard interactions, that epsilons, we don't care about where to put it because we assume you can put it anywhere. Because since it's a new interactions, it can couple new combinations of the real states. So you can, basically you can, since you are not bounded by standard model, you can have any kind of linear combination of these states, so we can put it anywhere. I don't know if that answers your question.
Well,
so it's any combinations. So any combinations of mass eigenstates will give different positions of those 3x3 matrices, which is written on flavor basis.
My problem is in the Lagrangian, because when you write the Lagrangian, the particle is written by the mass fields, but
yes, it was not written on mass fields on my Lagrangian, but again, it's just a matter of rewriting the Lagrangian in the correct way.
But
correct.
it's possible.
Yes, you can write it on with the mass eigenstates and put some coupling some interactions that sees a different combination of those mass eigenstates.
I understand. Yeah. Thank you.
Yeah, sorry for keep in the same topic, but now I understand that what we call electron neutrino or antineutrino is just a linear superposition of the mass eigenstates. And it turns out that the W boson likes to behave in the way that every time that it creates an electron, it produces that specific linear superposition. But that makes sense to call that electron neutrino when the arrow time goes in that direction. But in the other direction, I need that the neutrino be in that specific linear combination to interact with the W boson in that way. I mean, any other combination is just sterile to any kind of interaction. Because otherwise, the neutrino could be in any linear superposition and it have a certain probability to behave as an electron neutrino. But it's not what we call electron neutrino. I don't know if you understand what
So I think I understand the gist of the question. So the idea is that diagram is a property of the W boson. If you were talking about a W boson process involving an electron, all of the information you need for doing the calculation is there in the blackboard. What you're asking is, it's easy to see that when I produce the electron together with the neutrino, that I produce a specific linear combination of 1, 2, and 3.
Yeah.
You're asking what happens when there's a neutrino coming in,
Yeah, exactly.
and the answer depends on how did that neutrino get there? You know, what was the process that produced that neutrino? And that will tell you which linear combination of 1, 2, and 3 you have. And once you have a specific combination of 1, 2, and 3, like the example I talked about there, imagine you have the linear combination that we normally call the muon neutrino. In that case, I can do the calculation. And then I would get that the rate is 0. But I'm not using any information that's not there. I'm just using the information that's on the black. I mean, I'm not using any information that's coming from somewhere else. So just to say it again, when you're asking about a muon, when you're asking about a neutrino coming in and hitting something, it is always the case that you have to specify your initial state properly. And maybe that's what Pedro was thinking. I was thinking the same thing. When you're talking about solar neutrinos, the thing that comes from the sun for high enough energies is not a specific linear, it's not the electron neutrino. It's actually a neutrino number 2. And the question is, what's the interaction of the neutrino number 2? It's again given by this diagram here. The neutrino number 2 knows how to produce an electron, and the coupling is proportional to UE2, which is why in that plot up there, the survival probability bottoms out, and the element that shows up there is not exactly UE2 squared because there's some extra complication that we don't want to talk about, but it's exactly almost UE2 squared. Again, I showed this before as well. The extra complication has to do with the fact that the analysis was done in a 2 neutrino framework. You have to remember that there's a 3rd neutrino, and the overall effect of that, in many quotes, is to take a little bit of your flavor, hide it in the 3rd neutrino. That component doesn't do anything, but that means you have less neutrinos for the neutrino number 1 and 2. So that's why you get this extra cosine squared theta 1,3 factor. But that's exactly what happens. So there are circumstances under which the thing that hits your detector is not this linear combination or the electron-neutrino combination or the tau-neutrino combination, but it's something different. And in the case of solar neutrinos, it's a neutrino number 2. And there are many other cases where we believe that the neutrino that will hit your detector will be a mass eigenstate directly. We haven't talked about this at all, but we believe that the best way to describe neutrinos coming from a supernova is an incoherent mixture of mass eigenstates. We also didn't talk about that, but we've talked about the cosmic neutrinos that we've never seen before. But if we were lucky enough to see one, we believe that the best way of describing cosmic neutrinos is as an incoherent mixture of neutrino number 1, neutrino number 2, and neutrino number 3. Actually, that's how these cosmological bounds are derived. Nobody's talking about oscillations of cosmic neutrinos. They have long ago, went their separate ways, and they just look like an incoherent mixture of mass eigenstates. And as people have asked, if you have a non-standard interaction, the non-standard interaction produces some other unknown linear superposition of mass eigenstates. If we could use the non-standard interaction to produce a neutrino, that would be the neutrino we would have to talk about. And not surprisingly, that neutrino can produce an electron if it hits something, and it can produce a muon, and it can produce a tau. And the coefficients associated to that will be related to these epsilon parameters that Pedro showed. And again, you can write down your Lagrangian using whatever basis you like. And in the case of the non-standard neutrino interactions, using the flavor basis is really convenient. So we use that one. If you want to use the mass basis, you're welcome to do that. And they're related in a way that we all understand. It's just this U matrix. So this U matrix is a thing that allows you to move from one basis to the other. So in your Lagrangian, you can write down the neutrinos in any basis you like. And there's nothing wrong about that. It's totally fine. The only statement I'm making is that the propagating neutrino states are the mass eigenstates. Other linear combinations are not. So that's kind of the main point.
So my question is for Farinaldo. You made the plot of the mass of the particle, the dark matter particle, and the cross section, and you said that the asymmetric dark matter would be in a range of 5 eGV. And let's suppose that we detect it. How would you know that it's exactly the asymmetric dark matter candidate?
That's an excellent question. So, so there are signals. Are you going to talk about asymmetric dark matter annihilation from the sun? Just asking Fabio. Fabio, are you going to talk about?
Asymmetric dark matter.
Yeah,
well,
asymmetric.
There's no.
No? Okay.
If we have enough time, I will explain how anything that has a weak interaction can accumulate inside the sun. But I can answer now.
Yeah. Okay. So for instance, there are some signals. Naively, you cannot say.
So can I ask you
Yeah,
a question?
sure.
That is, how do you detect it first? That's the thing.
Yeah.
Okay. So that's the first problem.
So
You detect something. It means you either see a scatter in a direct detection, which I'm going to talk about, or that's it. Because if you're talking about asymmetric dark matter,
yeah, if you're looking for asymmetric dark matter, for instance, the annihilation of asymmetric dark matter today is really suppressed because you don't have particles and antiparticles today annihilating around. If you observe a signal of indirect dark matter detection, that will be the things that Fabio will be talking about. If we see, so the vanilla, always be careful, the vanilla asymmetric dark matter models, gone. The vanilla ones. If you ask someone who proposed that model, for instance, such as Catherine Zurich, she'll say, no, it's not. Well, I can twist around a little bit and still observe an indirect dark matter detection signal today, as far as gamma rays are concerned. Okay, you have
so sorry, no, I did not want to interrupt. I was thinking aloud. So maybe we can take the question tomorrow, because I think it raises more. You're saying if I detect asymmetric dark matter, how I'm sure, okay? And I would capsize the question. I would say, I detect something. How am I sure of that something, what it is, right? And tomorrow's class is more or less the idea of guiding you through everything we've studied, how it connects to the theory, but then how it shows in the experiments, which are the focus of next week. So the idea is to capsize. What you do is to observe. What do you observe? And then how you reconnect it to everything else you know, which is your question. It's just seeing it from a different angle. Yeah. But you need tomorrow's class for that. Otherwise,
but one thing is true for sure. If you observe a signal, if it's around 5 GeV, you want to say, for now, to observe a signal 5 GeV, the first thing that will come to my mind is asymmetric dark matter. If it will be asymmetric dark matter or not, that's another thing. What will come to my mind is asymmetric dark matter. So but then we have to use the dark matter complementarity of different signals to determine whether or not asymmetric dark matter, because asymmetric dark matter has some properties to say, well, I expected this signal in direct detection experiments And this signal should not appear in indirect dark matter detection, or should not appear at LLDC. So you start using these data to rule out or not the hypothesis of being asymmetric dark matter. Because the WIMP can also give you a signal 5 GeV. That's okay. Prism can also give a signal 5 GeV. But if you see a signal 5 GeV around 5, I mean, this is a huge coincidence. I would say I would bet it would be asymmetric dark matter.
I have a
Me?
question
Okay.
to Farinaldo. And you talk about the WIMP miracle. So if I understand, you fix the cross-section of a particle with the abundance of dark matter. So we have a lot of candidates. They all have that same cross-section?
No. So for the WIMPs, old relic, thermally produced, yes, that the cross-section is around that. Other candidates, they might have totally different cross-sections, from super tiny, from super large. Okay, so for WIMPs, thermally produced, vanilla WIMPs, that's the cross-section.
Won't change the abundance of the...
Yeah, so the cross-section is related to the abundance directly. But there are some caveats, the ones I've shown, the 3 caveats, then you can still change a little bit that result. But once you fix the cross-section around that, the order of magnitude, you also know the order of magnitude abundance is related. You cannot go beyond that. So in the WIMP vanilla model, the only way you can go beyond that is through these 3 exceptions I've shown for the WIMPs. Vanilla, thermally produced.
Again, if I can reverse the argument, also because you're very young, so there are sociological aspects to the problem, okay? So the way it happened, and then people identified what's the miracle, is that on one hand, people had the cosmological abundance of dark matter. That comes from observations of large scales in cosmology. On the other hand, people had created supersymmetry, which is something which relates to the electroweak scale, not for creating dark matter, for entirely different reasons, okay? And then that's something that goes around the electroweak scale. And then said, ooh, I can have some flavors of supersymmetry produce a stable partner, which could be the dark matter, okay? Then they say, so these are 2 separate things and they're just starting connecting them. And then they say, okay, but if I have these sort of candidates, they might be thermally produced. And I know that the thermal production mechanism will give me a different relic abundance if I have different cross-section. What happens if I put my scale, which is the electroweak scale, into the production? What's the order of magnitude I should get? Oh, it's the same order of magnitude in the relic abundance that I get from cosmology. Miracle, okay? But then you go to the details. Yeah, but the vanilla model arises like that. And also because 30 years ago, it was connecting 2 problems that were not thought to be necessarily the same.
SUSY is much older than this omega of 0.3. So the omega of 0.3 you realize like much, much later. So before we were just thinking this weak scale cross-section was well defined a long time ago. So I used to write papers in the very early when I was PhD, omega varying from a very, very large range. Yeah, so and it was still a miracle. So today it's like the abundance of dark matter is about 27% of the energy budget, and it's 27, it's not 20, and it's not 50, it's 27 around that. So before I was, let's see if it's 20 or 60 or something.
Just in the end of the class, you put the exclusion plots on the board.
Mm-hmm.
So, and you, I don't know, I got the impression that everything is possible. But when we are moving towards to search for low mass dark matter.
Mm-hmm.
But what's your opinion?
So
What
in
do you
that
think
plot,
everything is possible, or
no?
there
In
is
that
some
plot, I was
preferred?
just showing you a bunch of candidates at the same time. So different candidates will give you different predictions on that plot. So when you cut some regional parameter space, now it starts favoring one model or one candidate over the other. So that's all you're saying. So sure, I can go to things, regional parameters way beyond that plane if I come up with a new candidate. So I could Martin, Darky Martin. You come up with this Darky Martin candidate, and they might be in a different regional primary space. But that's why I have many regions, just because I'm playing around with different dark matter candidates that go different from what you were saying. The cross section, so forget about WIMPs. Maybe it's light dark matter, very, very, very light. And then that will not even pop up in that regional primary space, but it's a different candidate. The production mechanism might be entirely different from WIMPs.
But why would you just say what is the preferred candidate, or you would say no, it's everything is possible?
No, I wouldn't say that everything is possible. So as a theorist, I would try to come up with something from guiding principles. Now say, let's see, there are two approaches to that problem. So the experimental approach, whatever you can observe, you go after it and see if you can find. And from the theoretical perspective, I would say, let's see if I have a compelling model and I can predict something. So these somethings can be these masses around EV to GV up to TV, or be around that area. So I wouldn't go much further than TV, and I would go much below 1 MeV or so. So usually, just because I'm being biased, the models I've worked and I've read about, by construction, you expect this dark matter mass to be around that. I can go beyond that, yes, but I wouldn't, from the first principle, without seeing the data, no, I have a model where the dark matter mass is this very light. It's super fine-tuned. Can be, but it's fine-tuned. Just let's see these ballpark approximations that I was doing. Order of magnitude approximation, then you expect the dark matter to be so light, like 1 EV. I mean, it's really, really hard. It might be nature. I see, one thing Manfred Lehner once told me, he's not around, so he's recording, he might complain. He says that nature is a female word, so she does whatever she wants. Okay? So that's how it goes.
Here.
Are you going to comment on them? Okay. So let him clear. Okay.
I have a question to André. It's about sterile neutrinos. In the 4 neutrinos approach, we have 4 interaction neutrinos, and it's looked like that the sterile neutrinos is a state that takes account to the lack of events in the process. Well, in this view, it looks like this is because the unitarity of the mixing matrix. And why we should have a unitarity mixing matrix?
So that's, there are lots of layers to this question. The very pragmatic answer is, of course, if you have a 4th mass eigenstate, then you write it down over here. And that's the end of the story. So you can do all of your calculations back again. In this case, you have to be very careful now with the Z coupling, because the Z coupling now becomes weird, right? Because the Z coupling, and the reason, there are different ways of thinking about why this is a unitary matrix. They all have to do, deep down, they have to do with gauge invariance of the SU2 theory, and the fact that in the flavor basis, we know how the W and the Z couple. So that we know for sure, and it's a very important fact, because that's a gauge theory, that the W and Z couplings are the same, we have the same strength to the electron, the muon, and the tau, or to all of the different neutrinos. So it's the fact that all those couplings are the same, that when you go out and you change everything into the mass basis, that change of basis will induce these effective couplings here, and you can convince yourself that all these numbers have to add up to 1, the squares of them have to add up to 1, and all of their dot products are 0, right? So this object here will be 0. So all of this is a consequence of the SU2 gauge invariance, and the fact that you can re-express everything in terms of these mass eigenstates, let's say. So that's kind of one short answer to that. I was going to say something else, but it escaped me now. So I'm not going to say that, so I won't say anything. But that's kind of so it's a combination of those two things. And again, it's always because of field redefinitions, right? So you're always, I remember what I was going to say. It's all about field redefinitions. It's the fact that when you write down your model, which has a bunch of fields in it, you can always rewrite it by choosing a different linear combination of fields. You can pick whatever linear combination you like. If you want to get into a lot of trouble, you can pick norm-orthonormal linear combinations, and then life will be totally miserable. So you don't want to do that. And again, usually the guiding principle for that is the kinetic energy term in the Lagrangian. You don't want to screw around with that, because then it's really hard to figure out what's going on in your theory. That's kind of one. The other comment I wanted to make is a following interesting comment, which is notice that if you use this language, and if the thing that you're calling the stereoneutrino doesn't interact with anybody, there will never ever be a time when you're doing a calculation that these objects here will show up. You know, because these are if you want, in this language here, these would be the couplings of the W boson to a fermion that doesn't exist, which is this stereofermion, the stereo-charged lepton, which doesn't exist. So these objects here would never show up. You can write them down to make the matrix look unitary enough for you, but they're not physical objects that you can measure in your theory. This has interesting consequences if you think about a model with lots of stereoneutrinos. So if you have a model with lots of stereoneutrinos, you would say, hey, now I have a mixing matrix that's 5 by 5. Let's count how many mixing angles I have. And you're going to get a lot of mixing angles. And you will be able to convince yourself that some of those mixing angles don't really exist. That means that they're not possible to measure. They will have something to do with mixing angles amongst the different stereoneutrino states. But since you can't measure any of those, you can't talk about them mixing with one another. So there's something, when you talk about a stereoneutrino, this language here still applies. You can still construct your unitary matrix, and you can use all of the oscillation language that we've been using and the mixing language that we've been using, and it's completely fine and it's the right way to do it. But you will find out that there's some funny features associated to unitary matrix, especially once you start having more stereoneutrinos. You will find out that there's a lot of stuff going on in your matrix that's completely unphysical, and you can take advantage of that to make your life simpler. So that's something else to think about. But again, yeah, that's why I think Rolando said this. Once you start having stereoneutrinos, the best way to think about them is to think of them as extra mass eigenstates. So you're looking for new mass eigenstates that also couple to the W boson in some reduced way, because that's the thing that you get to measure. The stereoneutrino part, you never get to measure, because unless it has some new interaction, which of course is a possibility, as Pedro talked about today, to try to resolve this n effective equals 4 problem, for example. Okay, but again, the nice thing about thinking about it this way is that it's easy to generalize, and you just have to keep in mind that once you generalize in this way and you don't have more charged leptons, then you have to be very careful about how to properly write things down. And this is especially true for the Z coupling. So I encourage people to sit down, write the Z coupling in the mass basis, and see how the unitarity of the 3 by 3 matrix plays a very big role to make that coupling diagonal, and how if the matrix all of a sudden is 4 by 4 or 5 by 5, you no longer have all of the Z boson couplings be the same and diagonal. You can have a new 1, new 2 coupling, something like that. Okay, so I think that sounded right. Okay, so I'll stick to that. But it's a great exercise to do, and it really helps understand all of these subtleties as well.
Okay, so we're running out of time for the discussion sessions. We can take one question more. Otherwise, I remind you that, okay, good.
Since the last discussion section, we'll
Actually, we have tomorrow. We do have a discussion session. So.
okay, but could somebody comment on the blazer detection of the neutrinos?
Blazer detection.
Do we have time next week?
Tomorrow we have a discussion session after Eduardo Ponton's talk. So it's 3:45. Yeah. But besides,
You're talking about it in a lecture.
So regarding your question, he will answer during the talk. But also we'll have like a 1-hour discussion session tomorrow where we don't have exercises. So today's last day of exercise. Okay. Yeah. Before we go to break, I will ask if someone found a telephone charger that I think Diana Sandoval forgot yesterday in one of the rooms downstairs. So if someone found, okay? For the afternoon, we'll do as yesterday. I heard good comments, both from the speakers and from the students, that it worked out nicely. So we do exactly like yesterday, except that you switch rooms, okay? If you were on one room, you go to the other, and the lectures keep in the same room. So basically, you switch subject, right?
Make it escape room.
Escape room. I like that idea. That's good. So it will be locked, and once you find the solutions to all the problems, you'll be able to leave. But you can work collectively to get to this answer, right? After the coffee break. Yes. Yeah. So now coffee break, half an hour. If you want to leave your stuff here, then after the coffee break, we split into 2 rooms, exactly like yesterday, okay?